Hi everyone, and thank you for joining me today. Today's topic is going to be the ins and outs of threads by GoEngineer. My name is Adam Lundgren. I am an applications engineer with GoEngineer. I am based out of our headquarters in Salt Lake City, but if you've got questions and things on SolidWorks, I left my email up there. You can feel free to email me and talk to me at any time. Now, the thing that we're going to be talking about today, I've pulled up an agenda here. We're going to go over the 3 ways to create threads in SolidWorks. We'll also talk about the pros and cons of physically modeling threads. You'll note I put performance there in parentheses because that's the most important thing. And I know for a lot of us, McMaster Parts are the synonymous thing that we think of when we are talking about threads and toolbox parts. So we're going to talk about how to edit those. We'll talk about the various considerations for drawings and FEA, and then finally 3D printing. So when talking about making threads, I'm going to go through 3 different ways to make the same part, particularly this threaded insert and this bolt. Now this will be a custom bolt and a custom threaded insert. And of course I have these models myself, so if you've got questions on those, feel free and ask those. Now the first method is sweeping along a helical path. This is the original method, so anybody that is familiar with SOLIDWORKS and has been using it since its inception, this is the method that they would use or they would have learned. What we're going to do is we are going to create a helical path, and then our profile is going to sweep along that path to create our threads. So the first thing we need to do is we need to gather the necessary measurements to create our threads. So we need to get stuff like the major and minor diameter and all that stuff. And the way I did this, if your company works with threads already, they might have a table similar to this, but I know I'm going for a 3/8/16 type thread. So I use the mighty interwebs to find a table that would be useful for me, and it's going to help me grab the appropriate dimensions. So again, I'm going to be making a threaded insert and a bolt that goes into that threaded insert. So I need to note things like the profile base being pitch over 4, the height of our threads, and the fact that our minor diameter is the major diameter over 2. So the first thing I'm going to do is make our initial geometry, some simple stuff here like extrudes and revolves and some patterns. So I just start with this initial geometry, and we're going to create the threads at this point. So to create this thread, I'm going to create a sketch on the front plane. It's going to be right on the edge of this hole there, and I'm going to start with a center line. Now this hole is going to be the minor diameter that we saw on the previous chart. So we pierced the hole, and this is going to be where the helix starts. Now if you're familiar with swept cuts, you know that our profile has to intersect with some point on the path, and it's going to follow it around. So this is our profile sketch, and you're just using the same measurements that we saw on the previous slides. So you can see we started with that center line that pierces the where the helix is going to start. You can see we've got that 60-degree profile angle. We've got the profile land, that's the pitch over 4. The profile height's just the diameter difference between the major and minor diameter. So once we have that, we move on to creating the helix from the circular sketch. So all we're going to do is convert entities on that inner edge here. And so once you've done that sketch, you can see here I made sketch 19. You're going to start a helix feature using that sketch. You can see I can define the pitch and all of that. I'm going to have this go through far beyond our threaded insert, so that when we go into a cut sweep using that path and that profile, you can see it cuts through well beyond that profile there. And we can do this because it's a cut. If this was an extrude, we would have to worry about trimming some of that external material. So yeah, it's important to note that you can create material and also remove material using this method. Okay, but there is a new tool, something newer in 2016. So I suppose it's not all that new, but it's the thread tool. It's going to do a little bit of this work for us. It's going to save some time for us, especially in creating these threads and thread profiles. So let me show you how to do that here. I'm going to open up SOLIDWORKS and I'm going to create a new part. Okay. So I have this custom bolt part here. This is just a template. It doesn't have any information in it. So what I'm going to do is I'm going to start on the top plane and I'm going to make a hexagon. And we'll go vertical for that. And then from edge to edge, we'll grab that dimension. This hexagon is going to be 9/16 inches. And with that, we can just extrude this out, 1/4 inch. And now our custom bolt has a little washer here and then the actual stock that it's threading. So I'm going to do that all in one simple revolve feature. I'm going to make a sketch on the front plane using lines that start here at the midpoint, go out, over, back and up, over and down. And we'll make this our center line here so that we can revolve around it. Okay, so that's the general profile. Let's actually dimension it now. Well, we know that our washer is going to be 1/16 inch deep. So we place that. We know that the washer has a diameter of 0.81. This here is going to be our stock that has a diameter of 3/8 inches, right? So, and this has an overall height of 2 inches. Okay, so that's going to be the thing that we revolve. So we go ahead and do that. All right. So when we go to our thread tool, which is just here in the drop down for hole wizard, we get this notification saying, hey, thread tool that we're going to be using, the thread profiles that we're using, it's not for production quality. So if you wanted some for production quality, you'd need to make them yourself. So what the thread tool does is it uses thread profiles that already exist. Things like we've got inches, we have all these different sizes. It has these thread profiles to create a sweep for us. And it does so by making it it makes it so that we don't have to draw that thread profile ourselves. But if we're going to create a custom thread profile, we need to know how to do that. So let's do that right now. I'm going to create a brand new part using a part template in inches. And I'm going to just draw that thread profile sketch on the front plane. That way we can use this over and over once I've made it. All right, so to create that custom thread profile, like I said, we're going to be starting with a center line to find that pitch. Okay, so we have that center line. Let's go ahead and dimension it. Now we know that the pitch for the 3/8 is 1/16. So let's go ahead and call that. And let's go ahead and looking at here, this is called a pitch. And I'm going to want to see what my dimensions are called. So there we go. Okay. Now let's go ahead and make the profile for our thread profile. I'm going to start and go up, out, down, and back. Now to follow that chart I was looking at previously, I need to go ahead and make this a little bit symmetric. I'm going to add a center line to accomplish that. Just by adding this center line from midpoint to midpoint and making it horizontal. Now we just need to finish adding all of these dimensions. So we know that this is 60 degrees, for example. we know that the profile land, is the pitch over 4. So let's actually use an equation here. We grab that pitch and have that over 4. All right, and our profile height is going to be our major diameter, which is 3/8, minus, let's see, I recall it being like 307.3. And then remember, this is a diameter, so we have to divide this all by 2. And that's it. That's fully defined. So our sketch is complete. This is the profile height. And y'all get the idea of what this all should look like. So this is our profile sketch. Thread profile is complete. Now I'm going to go ahead and save this. The rest of the thread profiles. So I'm going to select the sketch and hit Save As up here. And we're not going to just save this as a regular part, we're going to save it as a library feature. So choose library feature part, and SOLIDWORKS will kick us to the default location for a design library, but this isn't a design library part, this is a thread profile. So let's go back a folder to this thread profile location. Now this is the default location, it's just this right here. If you want to add your own location, you would need to go into settings to do that. Now we already have a 3/8/16, but I'm going to go ahead and name it this anyway. Now you can see that this has become a thread profile. You see the library feature indicators, and that's all that we need from this. We can access this inside of our thread tool now. So let's go ahead and go back to this. And a key thing to notice when we use our thread tool is that right here in type, we can see my custom 3/8/16. We can choose a size. Now we only have the one size. This is default. These sizes are the configurations. Now if we go back to if we go back to the library feature part we just made and made different configurations, those would be different sizes and they'd show up here. Kind of like how with this one there's all these different configurations. But we'll just use the 3/8/16, the one size. And we're going to start our thread location up here at the top. It's going to go up to our selection right here. So it's going to cut a thread all along here. And if we wanted to cut, we could select this. And if we wanted to extrude, we would select this one right here. And we can flip it to make it go the right direction. But because we made it 3/8, this is going to be another cut. And now if we pay attention up here, the thread starts up here and goes down. So we need to offset this up 1 pitch. So I'm going to select offset indicator right here, and I'm going to offset this off 1/16, which is the pitch size. And you can see it offset in the wrong direction, so I'm just going to flip the direction, make it go the right direction. And that is going to come down for us. So I'm going to say OK. And there we go. We've got our physical threads. So let us go ahead now and take a look down here. You can see it removed a bit too much material. We just do a convert entities and just extrude back to this surface. And that's going to fill in that material once again. All right. And when it comes to this chamfer up here, we can't use our chamfer tool, because if we were to chamfer this up here, I mean, it's not going to work the way that we want it to. So what we're going to do instead is we're going to create a cut revolve, and starting with a sketch. So we create a sketch on the front plane, and let's create a center line. Since this is a revolve, we'll have a center line going up through the center. But when it comes to the lines that we'll be making for our revolve, it's just going to be a simple triangle, 45 degrees all around. We'll set those equal, we'll add that relationship, and that'll make sure this is 45 degrees, and we'll dimension it. We'll say 0.1 inches here. We'll say 0.1 there. And yeah, now this is fully defined. Okay, so this is going to go all the way around and give us our chamfer. Let's do a revolve cut. And there we go. That's our chamfer that starts our bolt here. Okay, and that is all we need to do when it comes to our custom bolt. So we can save and close this. All right. So that was the second method in creating threads. The third method is a cosmetic thread. Now this is different from physically modeling threads because we are not actually physically modeling threads. We are just drawing a circle and saying, hey, there would be threads here. These are the sizes, and it is a very useful, it is a really useful tool within SOLIDWORKS. So let's see how that's done. So what I'm going to do here is we're going to create a new configuration of this bolt here. We're going to create that configuration called Cosmetic Threads. So we're going to suppress the features that we just made, and we start the Cosmetic Thread tool. And now what we're going to do is we're going to select the size. So what the Cosmetic Thread tool is it's deep inside the drop down list. So what I tend to do is I tend to use the command search bar in the top right corner. But if I recall, it's inside insert annotations, cosmetic threads. So, I mean, I guess it's not too deep, but what we're going to do is we're going to start with this edge that we're going to create a cosmetic thread to. And I've selected to go through the part. Okay, now we can choose the standard here, which is this is an inch, and this is a 3/8/16 inch machine thread. Now, what if you have a bizarre thread type, maybe something that's not in the ANSI standard? We do have the alternative to make a custom thread callout. We can just choose the depth of cut and all that. We can choose the end condition, what the thread callout would be. Now, this thread callout is important for, say, the drawing. It'll automatically pull this up. Okay, and that's how we make the cosmetic threads. Now, if we carry on, what are some of the considerations we need to make when it comes to performance when we talk about these threads? You can see all the pros here. It allows 3D printing, you get accurate mass property calculation, it'll actually do FEA for these threads. But the biggest con of physically modeled threads is that it has a negative performance impact on the system, and it does so in a big way. You can see my admittedly satirical example here on the right, where it says the file was last opened in 83 minutes and 29 seconds. But it is really only slightly satirical. When you open an assembly that has many threaded parts, you are going to see slowdowns. Your frame rates drop. It'll take longer to open. So let's actually take a look and do an example. So if I go ahead now and open up a sample board here, right? This board has a bunch of holes here. It's a perfect size for our threaded inserts. We'll insert that in here now. Or actually, we need to create an assembly for this first. So I'm going to go ahead and make a new assembly from part in inches and just place that down. All right, now we'll insert our threaded inserts. Let me flip that around a couple of times. Mate that up with our board here. We'll use SmartMates for that. Okay, now because this was all done in a couple of patterns, we're going to use pattern-driven patterns. So I'm going to grab that part, and we're going to grab the pattern that we're going to copy it to. And then we're going to do that one more time for the rest of the holes. All right, so we have all these threaded inserts in here. Now let's go ahead and add in our bolts. All right, now I'm going to flip this around a couple times, and I'm going to once again use SmartMates to locate it. Okay. And let's go ahead and add that to our derived pattern here. And that should add it everywhere. Yep, there we go. Okay, so this is our assembly. It's done. Now, let's go ahead and save it. And let's go ahead and call this performance because that's what we're looking at here. Now I'm going to close it and just open it again and take a look. And let's make sure that these are on physical threads. Okay, I'm going to close this and reopen it again. That way we're going to see the timer and how much time it takes to open. And we're just going to open it back up. Okay, so going into evaluate and looking at performance evaluation or assembly visualization, we'll look at performance analysis here, which basically is a visualization of the performance evaluation. But we can see over here the SOLIDWORKS open time and rebuild time. So all of this added together, we are still shy of a second, but note that this is an assembly that has less than 400 components, and the fact that we're already nearing a second should be a little frightening. But yeah, just the total number of graphics triangles. It's several orders of magnitude higher than if we didn't have threads. So every time we hit the rebuild sign, the stop sign up here, we have to wait almost a second. So what happens now, instead of our physical threads, we use our cosmetic thread. I'm going to change that configuration here. I do that for the threaded insert and bolt. Now let's once again take a look at the open time. I'm going to save and close this and just open it back up again. The open time is a little bit faster. I mean, that was something I noticed, but let's not take my word for it. Let's take a look at this performance evaluation. Okay, notice the open times are, again, orders of magnitude less. Our rebuild times are much, much shyer than a second, probably closer to 1/8 of a second. Our open times, we've still got a little bit of an open time, but overall the performance of this is vastly improved. If I were to take a section cut, for example, of this area right here, it does so pretty quickly. You'll notice, because we did cosmetic threads, that they interfere here. But if I were to now once again go and use physical threads, if I were to do that exact same section, we're going to be waiting here for it to process that a little bit. Yep, notice the time here. So that is, I mean, if we want to demonstrate one of the key reasons why we use cosmetic threads over physical threads, then this is it. I would say, unless you have a special case where you need to make use of one of those pros that I was talking about in creating threads, let's probably line this up better, but I would stick with cosmetic threads just for the performance benefit alone. Okay, so let's head back into our presentation. All right, now what about McMaster screws? We saw the benefits of using cosmetic threads over physical threads, but that is obviously performance. And if we download from McMaster Car, it looks like we have 3 options here. There's a SolidWorks, or a step file, or a step with no threads. Now the step with no threads, that'll all come in with no threads, and you can use Cosmetic Threads straight away from that. But what happens when we download SOLIDWORKS? Well, they do have a threads folder here. You can just suppress it, and that will keep the main shape of the bolt minus the threads. From there, you can again use Cosmetic Threads to fill out a drawing if you need to. I don't know why you're making a drawing of a McMaster screw, but now what if we get a step file, or what I like to call a dummy solid? There is a command called delete face, which, if you are not familiar with, we have several pieces of content on how to use delete face, but all you have to do is select the face of the thread, and we're just going to use delete face to patch it up for us. So we go from that to this by only selecting those threaded faces. But now what happens when we take these threaded parts and we put them into our drawings? Well, you actually have the same considerations as with assemblies. You've got huge performance. In fact, you might even say it's more because you're inserting that assembly multiple times, so you'll have greater concerns with performance. Once again, it's important to iterate that it's most of the time better to use Cosmetic Threads, especially in this situation, not just for this reason, but for one more that we're just about to see. Okay, so we have our threaded insert that we were just looking at, and we've inserted that into a drawing. Now, when we try to use smart dimensions to call out these threads, we are going to see here that it calls out the 3/8/16 machine threads. And this was really easy to do. We saw this clear back when we made the Cosmetic Threads, where we could choose the call out. This is where it shows up. It's just taking that field that we entered and putting that into our drawings. Now, remember this threaded insert, we use the cut sweep methods, that original method. When it comes to dimensioning the threads with the physical threads that way, what we'll have to do instead is we have to create a note, because that threaded callout doesn't exist. It certainly doesn't exist in this method because all it is a sweep. There isn't any data that way. Now we'll still get an accurate height and accurate measurements and all that, but there's a little bit less convenience when it comes to this thread callout. Now going back to the Cosmetic Thread for the bolt, you can see we can view and measure the Cosmetic Thread here, and the whole callout and the thread callout comes out like so. Now, there's actually no difference between the thread command and our original cut sweep method. You can see this bolt, it was created with the thread tool, but we still have to create a note. It doesn't automatically generate a whole callout for us. So, especially when it comes to drawings, it looks like Cosmetic Threads are our way to go. Now, when we talk about FEA, and we've got threads, oftentimes we've got assemblies and fasteners and things that hold things together. Many times those things have threads. So what do we have to think about? Well, anytime we are actually doing simulation of physical threads, we have to refine our meshes to a very large degree near those threads. And that's to make sure that it's accurate. Now, of course, this is going to make it so that our simulation takes longer to run, longer to mesh, and it's just going to take a lot of computing power and time. And especially when you're trying to meet deadlines, it's all about how much time we're taking to do some of these things. So we do have the capability of using FEA to test the strength of our threads. Can they withstand the stress of what they're doing? But most of the time these are rated, which means we're going to be looking at suppressing these and entering the connectors. So rather than actually have the connectors physically in the mesh, we can instead have connections exist to replace these fasteners. Now, as the top bullet point says, you can automatically convert if you're using toolbox components. Now, these components are not toolbox components. That's a topic for another video, but you can see if they were, we would have the option to convert these toolbox fasteners to bolt fasteners. That'll suppress these and bring in bolt connectors that'll be used for our study. Alternatively, we'll do that ourselves. We will suppress and then manually enter that connector. And that's just because they're not toolbox components, so we'll have to do that manually. All right, now finally, what if we want to 3D print a prototype of our custom threads? What do we have to think about there? Well, first and foremost, physical threads are needed to actually be modeled in order to print, because you can't 3D print cosmetic threads, you know? You gotta have those physical threads. That being said, and this next thing is mostly a printer issue, we need to make sure that our printer resolution is at least 4 times smaller than the thread pitch that we're trying to print. If it's any larger than that, then we have to retap that ourselves. The goal is to get 5 layers per pitch or more, and with this, the more the merrier, the finer the resolution, the better. That is it as far as 3D printing goes. I obviously just need the 3D modeled threads. And that is it as far as all of our thread questions go. So it being the end of the presentation, I haven't seen any questions yet, but if you've got them, now is definitely the time to ask, and I will leave my email up there. If you've got questions you want to ask me privately, you can send me an email. And for those of you jumping off, thank you for joining me, and I hope to see you sometime soon.